Welcome to the lecture series of Basic Electrical Engineering. The subject code is ECE 101. The topic of today's video lecture is numericals based on EMF equation of a transformer. First numerical is a 2000 by 200 volt 20 kilovolt ampere transformer has 66 turns in the secondary. Calculate primary turns, primary and secondary full load current, neglect the losses. So we will solve this numerical by the method. First of all, we will draw a transformer. So according to the numerical, it is given that 2000 voltage V1 is equals to 2000 volt and V2 is equals to 200, that is V2 is equals to 200 volt, and if we are connecting the load, then the kilovolts across this are 20 kilovolt ampere and 66 turns in the secondary, means that N2 is equals to 66. So first of all, we want to calculate primary turns. As we know that from the transformation ratio formula, K is equals to V2 upon V1. From here we find out the value of K. As we know the value of V2 and V1, so it is 1 upon 10. So the value of K is 1 by 10. And we know that from the voltage transformation ratio that N2 upon N1 is equals to K is equals to 1 upon 10, or N1 is equals to N2 into 10, as N2 value is given to us 66 into 10, so we can say that N1 is equals to 660 turns. So the number of turns on the primary side are 660. Then second part is primary and secondary full load current we have to find out. As it is given in the numerical, neglect the losses. When we are neglecting the losses, then volts ampere on the primary side is equals to the volts ampere on the secondary side. So V1 I1 is equals to V2 I2 is equals to 20 into 10 raised to power 3 kilovolt volt amperes. 10 raised to power 3 means kilo. So from this formula we find out the value of I2. I2 is equals to 20 into 10 raised to power 3 upon V2 value we know that 200. From here we find out I2 current is 100 ampere. Similarly, we can find out the I1 current because losses are 0. So this equation V1 I1 is equals to 20 into 10 raised to power 3. So from here we find out I1. So it will become 20 into 10 raised to power 3 upon 2000, and we will get the answer 10 ampere. So we are getting the value of I1 and I2, or we can find out the I1 value by I1 is equals to KI2. We know the value of K is 1 by 10 and I2 is 100. So we are getting 10 amperes. So this is how we solve the numerical. Then we are having another numerical. In this numerical, an ideal 25 kilovolt ampere transformer has 500 turns on the primary winding and 40 turns on the secondary winding. The primary is connecting to 3000 volt 50 hertz supply. Calculate primary and secondary current on full load. Secondary EMF, the maximum core flux. So we have to find out the things accordingly. First we want to find out primary and secondary current. For this, as we know, the number of turns are given to us. N1 is equals to 500 turns on the primary side and N2 is equals to 40 turns. From the number of turns we can check that which type of transformer is it. On the primary side we are having the large number of turns as compared to on the secondary side, so this is step down transformer. So K is equals to N2 upon N1, it is 40 upon 500. So these are the number of turns. We make it as such. This is the ratio. Now for primary current, as in the previous numerical, we know that I1 is equals to volts ampere upon V1. So volts ampere are given in this numerical. It is 25 kilo volts ampere. It is capital A. Upon V1. V1 is connecting to 3000 supply. So V1 is 3000. We cut it with this, and when we solve this we will get 8.33 amperes. Similarly, we can find out I2. I2 is equals to I1 upon K. I1 value is 8.33 and K value is 4 into 50. So it is 104.2 ampere. Here the K value is 4 by 50 and 50 goes up, that's why I am writing it like this. So I1 and I2 values we have find out. The first part is clear. Primary and secondary current on full load means primary current I1 is 8.33 ampere and secondary current I2 is equals to 104.2 ampere. Then we are having the next second part. In second part we have to find out EMF equation. Secondary EMF means E2 value we have to find out, the maximum core flux. For this we know that E2 upon E1 is equals to K, and it can be written as E2 is equals to K E1, and we know that the value of K is 4 upon 50 and E1 is equals to V1, and we know V1 is equals to 3000 volt. So here we put 3000. When we solve this we will get 240 volt. Fine. Similarly, next we have to find out maximum core flux, means phi max we have to find out. We know this is third. We know the EMF equation on the secondary side. E1 is equals to 4.44 Fn1 phi m. So we find out phi m. Phi m is equals to E1 upon 4.44 Fn1. We know the value of E1 is 3000 upon 4.44 into frequency is given to us 50, and number of turns we find out it is 500, and when we solve this we will get 27 into 10 raised to power minus 3 vapor. or we can write it is 27 millivapor. So this is how we solve the second numerical. Then third numerical, a single phase 2200 by 250 volt 50 hertz transformer has a net core area 36 centimeter square. This is centimeter square, and maximum flux density is 6 Weber per meter square. Calculate the number of turns on primary and secondary. Means we have to find out N1 and N2. For this, we know that E1 is equals to 4.44 Fn1 phi m, and we know the value of E1. E1 is 2200 volt, because this value is given to us. V1 is equals to E1 and V1 is equals to 2200 volt. So E1 is 2200 volt. Similarly, frequency is given to us. Frequency is 50 hertz. Then we know that phi m is equals to Bm into A. Bm is the flux density and A is the area. So core flux is equals to maximum core flux is equals to maximum flux density into area. So what we have to find out? The number of turns. N1 is equals to here in this numerical, the net core area is 36. Area is given to us 36 and maximum flux density is 6. So 6 Weber per meter square into 36 centimeter square. When we convert centimeters into meters, then we can write it as 10 raised to power minus 4. So when we solve this, it will become 0.0216 Weber. So this is phi max. From here, area and maximum flux density, according to the formula, we put the values in this. Now we know N1 is equals to E1 upon 4.44 F phi m. Now we know all the values. We put all the values. N1 is equals to 2200 upon 4.44 into 50 into 0.0216, and when we solve this, we will get 529. So these are the number of turns on primary side. Then N2, similarly E2 upon 4.44 F phi max. E2 is 250 upon 4.44 into 50 into, this is the same value, and we will get 50. So N1 is equals to 459 and N2 is equals to 50. So this is how we solve the numerical. Next, the EMF next numerical is the EMF per turn of a single phase 2200 by 220 volt 50 hertz transformer is 12 volt. EMF per turn of a single phase 2200 by 220 volt 50 hertz transformer is 12 volt. Calculate the number of primary and secondary turns. The net cross-sectional area of core for maximum flux density is 1.5 ton. So we have to find out the number of primary and secondary turns. EMF per turn is given to us, that is 12 volt, and first we write down what is given to us. EMF per turn is 12 volt, then V1 is equals to 22 volt, V2 is equals to 220 volt, and we know that V1 upon N1 is equals to V2 upon N2 is equals to 12 volt. This is according to voltage transformation ratio. So number of turns, when we want to find out the number of turns, N1 is equals to V1 upon 12. We are taking this part, this is V2, means V1 upon N1 is equals to K. Means this is 12 volt. N1, so we put the value of V1. V1 is 2200 upon 12, and we are getting 18.33. As we are talking about the number of turns, the number of turns are the whole values, so the number of turns are 183. So N1 we have calculated. Then second is number of secondary turns, N2. N2, how to calculate N2? N2 is equals to V2 upon 12. V2 we know 220 upon 12 is equals to 18.33 or 18. So this is how we calculate the value of N1 and N2. Then the second part of this question is the net cross-sectional area of core for the maximum flux. So we have to find out the cross-sectional area. So for this, what will we do? Just I clear down the screen. Then we will solve it like we know that E1 is equals to 4.44 Fn1 phi max. Fine. We find out phi max is equals to V1, because we know V1, here we can write it is V1 is equals to E1 is equals to this equation. So we can replace E1 by V1. V1 upon 4.44 Fn1. It can be written as 1 upon 4.44 F V1 upon N1, and we know this is equals to 12 volt, so we can write it 1 upon 4.44 into 50 into 12. When we solve this, we will get 0.054 Weber. So but we want to find out cross-sectional area. Area is equals to, because we know phi m is equals to bm into area. So for area we know phi m upon bm. So area is equals to 0.054 upon 1.5, and it is equals to 0.036 meters square. So this is how we solve the numericals. This is all about the numericals based on the EMF equations. Thank you so much.